Alright, making another video. Just keep on coming. Alright, so, just thinking about this stuff, something occurred to me that I hadn't thought of before, that there's, two different devices, trebuchets and catapults, okay, and they basically are always illustrated as doing the same thing, which is basically, just throwing crap. And whenever you see a trebuchet, which is a gravity thrower, actually, you're moving a heavy mass into gravity and then you're throwing something, okay, by swinging the mass down below the fulcrum, all right, to throw something. Where a catapult is basically, you could use rubber bands, different things you can use where you're just really creating tension. You're just going to pull it back and let a spring throw it. So I was thinking about when you see these things illustrated in movies and whatnot, yeah, catapults are always the same size, and it just has a basket on here and it just throws crap. Whatever you throw in the basket, you don't move the basket anywhere, you don't do anything, you just always have the same size catapult and you just throw shit, essentially. Now, obviously, you can throw it higher or lower by moving it. Okay, so they probably did some of that, to change the arc, and get more distance if they needed it. But it's not like the trebuchet where you're always trying to get the stuff out further and further and swing it out, and so they can get very long. So trebuchets are very long, and catapults are usually kind of standardized in size. And so that's a distinction, but it's basically because this mass can only move, it's very limited in how fast it can fall, right? It can't fall faster than gravity. It can only fall slower, okay, than it would fall, the free fall, 9.8 meters. It can only go less than 9.8 meters. It can never go faster than 9.8 meters. So it can't really make this thing move faster. You can only change it by putting things further and further out, because you're really limited in how fast or slow this will fall. Now, this will fall slower than 9.8 meters per second because you are putting friction on it. You're applying a friction, and so you're going to slow down the speed. If you thought of it as a ball falling, you're basically just dropping the ball through a tube where you could constrict it. And so the more weight you put on, the more constriction you're creating, and the slower it falls down. So that's a real limitation of the trebuchet, where the catapult, again, we're right back to the spring arguments, okay, and rubber bands, and we'll have to think of what else you can store energy in. Flywheels, they can give you energy at any speed you want, okay, at any, fast or slow. You can use gears, you can use different things, but you can change the speed. So I just thought that was an interesting point to realize that, can't see my 9.8. Anyway, that I never really thought about what was the big difference between the two ways of doing it. One of this gravity thing has the huge limitation, frankly, of being restricted in terms of how fast you can actually make this thing move. And if you want something to be thrown faster, you have to put it out faster. You have to put it out further. Where catapults aren't restricted, you can just make more tension here, and this speed thing will really just depend on how much weight you're putting on it. And it just almost doesn't matter where you put the weight, except that will change height. But you'll end up changing the trajectory by changing what height you put it. So you'll change which direction it shoots it, but you can't really change the fact that it's going to push it at a certain speed, because it'll adjust the speed to the weight. When you put a light weight on, the springs will collapse quickly. Put a heavy weight on, they'll collapse slowly. So, I think that's of value for. I just never had that. I've never seen a video, never saw a document, never saw anything that explained the difference between those two mechanisms. And and it's a meaningful difference in terms of understanding what this limiting factor is, which is this speed problem. That we're saying we're putting the same force into a spring, and we're just assuming springs or rubber bands or some other device can adjust their speed to push whatever object they're going to push. Now, I think that's true. Okay. I think that they conserve momentum, but I also think that there is probably a liability in that they're all speed restricted. So as much as the gravity thing is really speed restricted, springs are also speed restricted. They can only move so fast. Rubber bands can only move so fast. They don't have an infinite speed. It doesn't go to infinity. So you could make the argument that yes, whenever you're moving something faster, you might be losing a higher percentage of the energy. That the spring might lose efficiency the faster you're obliging it to move. But clearly within a range that's well within the spring's comfort zone, it should be able to do the slow, heavy thing and the fast, light thing without losing any force. And we're really talking about force. Momentum is force, frankly. So you have to conserve it. I'm going to keep saying that because I think it's just absolutely true. If you lose it, it has to be somewhere, as Feynman would put it. It just doesn't disappear. So I guess I'll pause and see if I think of anything else. All right, back. I just thought I'd make, since I have the opportunity to do it, I might as well. In the previous video, which this is a clip from, all the way over there on the side, there's a little 85%, and I was talking about the percentages you could expect to lose when you put an object the same place on the lever. And the spring can adjust its speed, so it will just throw it at theoretically, the lighter thing will go faster, the heavier thing goes slower. And I'm arguing that momentum has to be conserved, so the light thing goes twice as fast if it's half as light. And what we can account for is losses, and the loss would be that, yes, if you force the lever to move faster, so the idea is the spring, the regular experiment, we're saying it moves the same speed, right? Technically this should move the same speed, this should be twice the speed out here, but the lever will move exactly the same. So with a 2 mass here, it moves the same as with a 1 mass out here. Same exact movement of the lever. So it's the same energy in the lever. So there's no losses. But in this case, when we put the 1 mass here and then we put the 2 mass here, the fact is you do have this loss problem because the 2 mass means the lever has to move twice as fast. The whole lever has to move twice as fast. That means this is 4 times the velocity out here, not just 2. But I indicated that that's still a problem for the 2 mass, and it's not a problem for the 2 mass. So the number would be still around that 33% number is what you're looking for, because the lever moves slower, so you're not losing energy to the lever's motion. The extra motion of going faster will be a loss to the lighter object, so you can't expect it to go twice as fast. It has to be something slightly less. I predicted 85%. But that's what you should get as a number. And for the low number, it wouldn't be the 25%. It would be something like 33% is what physicist Michael predicts. So 33% would be 33% or less, you win. For the half mass goes only 33% faster. More than 85%, I certainly win. More than 33%, we're somewhere in the middle. Then we can argue about it. Why did your theory come off wrong? Why did your prediction fail? Because both our predictions will fail. But anyway, so just a clarification. But yeah, there are all these little variables. It is the nuance of this is interesting. The whole idea of reflections, the whole idea of any dampening of the motion or the energy, and finding all the ways you can lose the energy are in fact lose it to the fact that you just didn't get it through the system quickly enough. All right.